Welcome to This Explainer. Today we're completely decoding the complex world of power system protection. We're going to take some, honestly, incredibly dense technical concepts and transform them into a really clear visual journey. Because if you've ever wondered how the massive equipment powering our entire cities keeps from just destroying itself when things go wrong, well, you're absolutely in the right place.
So here's our roadmap for today. We'll be hitting transformer fire prevention strategies, mechanical fault detection systems, electrical diagnostics and testing, differential protection relay logic, overcoming inrush current challenges, and finally, smart relays and CT failures. Let's get right into it. Okay, we're starting with literally the highest stakes imaginable in the substation: fires. I mean, think about it. A transformer is essentially just a massive metal box filled with copper windings and, oh yeah, highly flammable cooling oil, all operating under immense electrical stress. So when insulation fails, or if a massive electrical arc happens, that oil can ignite. You get a rapid spike in temperature combined with high voltage, and it is just a perfect recipe for a catastrophic physical failure.
Which brings us to Section 1, Transformer Fire Prevention Strategies.
Now, to put things into perspective, a single transformer fire, that can easily cost 2 to 3 times the price of the transformer itself. And we aren't just talking about the cost of swapping out melted equipment here. We have to factor in the massive power outages it triggers, the huge disruption to consumers, and of course, the collateral damage to the surrounding substation. That's exactly why power companies focus on preventing these fires first and minimizing their impact second. It's a huge deal.
This is where it gets really interesting. There's this unconventional but highly effective firefighting method that completely replaces traditional water sprinkler systems. Here's how it works. When a fire is detected, the system immediately isolates the transformer. Then a valve pops open to quickly drain the oil. It's literally pulling the fuel right out from under the fire. Finally, it continuously injects nitrogen gas into the bottom of the tank. This rapidly cools the whole system down, suffocates the flames, and absolutely prevents any reignition. It's basically a brilliant, completely self-contained rescue operation.
Moving right along to Section 2, Mechanical Fault Detection Systems.
So, there is a very clear division between our mechanical safeguards and our electrical tests. On the mechanical side of things, we've got devices like the Buchholz relay that covers both the main tank and the on-load tap changer, plus pressure relief valves. These mechanical components act as our first line of defense. They physically react to gas buildup or sudden pressure spikes way before we even start testing the internal electrical insulation.
Now for Section 3, Electrical Diagnostics and Testing.
Okay, once the mechanical parts are totally cleared, we move to the critical electrical tests. Things like tan delta and insulation resistance, which basically measure how well the internal components are shielded from one another. But here's the kicker. These must be done before any oil filtration takes place. Why? Well, if there's any moisture at all in that oil, it'll significantly alter your diagnostic results. You really want to capture that true, worst-case scenario of the insulation's health before you go in and start cleaning up the system.
Let's talk about percentage impedance, specifically when it's marked at, say, 10%. This single number, stamped right there on the equipment's nameplate, dictates the absolute maximum short-circuit current the system has to withstand. It's a simple but absolutely vital calculation. By dividing the rated current by this percentage impedance, engineers can predict the exact fault current during a short circuit. And that tells them exactly what rating their protection equipment needs to be to actually survive a worst-case scenario.
All right. Section 4, Differential Protection Relay Logic.
I always like to think of the differential relay as an incredibly strict accountant, but one that operates at the speed of light. Its whole existence boils down to one simple rule: what goes in must perfectly equal what comes out. If the current entering the transformer's protected zone doesn't perfectly match the current leaving it, the relay instantly knows, uh-oh, current is leaking somewhere inside that tank. It immediately signals an internal fault and trips the circuit to save the equipment. No exceptions.
But that strictness leads us straight to Section 5, Overcoming Inrush Current Challenges.
Because honestly, that strict accounting creates a massive headache when we're simply trying to turn the transformer on. When you first energize a transformer, it gulps down a massive amount of power. We call this inrush current, and this can spike 5 to 7 times higher than the normal operating current. To our super strict differential relay, this massive imbalance looks exactly like a catastrophic internal fault, even though it's totally normal and naturally disappears in less than a second.
So how do we fix that? Well, modern engineering solved it by looking at the current's unique fingerprint. You see, inrush current contains about 40 to 50% second harmonic frequencies. That means 100 or 120 hertz, depending on your local grid. And modern digital relays are smart enough to constantly listen for that specific frequency. When they detect it, they realize, oh, okay, it's just a startup surge, not a real fault, and they actively block the trip command. It's such a clever way to keep the grid online.
Finally, Section 6, Smart Relays and CT Failures. This brings us to our last major hurdle. What happens when the relay's own monitoring equipment breaks down? The relay gets all of its intel from current transformers, or CTs. But what if a secondary wire on one of these CTs just accidentally snaps? The current reading on that phase is going to instantly drop to 0. And remember our strict accountant? The differential relay will see that massive mismatch and could very easily misinterpret a broken wire as a catastrophic electrical fault. It would literally shut down a perfectly healthy power line.
But thankfully, specific smart relays, like the RED 670 for instance, act as digital detectives to solve this exact issue. Before the relay even bothers trying to figure out if a wire is broken, it checks the overall system load. It essentially requires the baseline current to be greater than 10% of the base current rating. If there just isn't enough power flowing through the system to begin with, the relay simply won't engage this specific diagnostic logic. It needs a solid, healthy baseline to even start looking for anomalies.
Okay, so once that 10% threshold is met, the relay runs through a rapid-fire checklist. It notices one phase drop to 0. But then it checks the other phases. Did their current spike like it would in a real fault? Nope, they stayed perfectly identical. Are there any 0 or negative sequence fault currents present? No. By verifying these highly specific clues, the relay confidently deduces that, hey, a wire is merely broken. It waits precisely 3 seconds, issues an open CT alarm, and blocks the differential trip. Boom. A simple broken wire doesn't cause a citywide blackout.
And there you have it. We've journeyed all the way from catastrophic oil fires down to the elegant microsecond logic of digital protection. It is genuinely fascinating to think about how these unseen digital detectives act as the true guardians of our electrical infrastructure. They're out there right now, constantly calculating, analyzing harmonics, and making intelligent split-second decisions just to keep our lights on. It really leaves you wondering, as these systems get even smarter, what level of revolutionary protection is coming to our global grid next?